showing the moment generating functions producted the independent random variables. But what we want to do now is think about what the things we've said about random vectors and matrices mean for the multivariate data, right? So specifically, what they mean for the multivariate data matrix. So let's think about properties of the sample. Properties. So in example 222 above, we noted that the rows of the multivariate data matrix rows, that is, of the multivariate data matrix X can be viewed as a collection and so the collection is a set of vectors xi for I in integers 1 to n, yeah, of independent, yeah, usually. Yeah, so we're only going to consider the case where they're independent. Yeah, random vectors. Yeah, so note rows are xi transpose. Yeah, because these vectors are columns by definition. Okay, and in the classical framework that we're going to do most of the work in, this is called a sample of size assumed to be a much larger population. Okay, so we've got a sample distribution and a population distribution. And a lot of what we're trying to do is use this small sample to make inferences about the larger population, right? So people on the stats courses should be quite familiar with that. So okay, so let's define some things for a sample. It's defined above, yeah, for a function. So G is a function that maps R P to R Q by R in general. Yeah. We write, and then we're going to use the angle brackets on this function G of X. Yeah. And so this works because we're assuming that all of the rows are sort of the same kind of X. Yeah, so it's a slight well, I'll talk a bit more about the notation in a second, then sort of the average by n of G of each of the X i's, right? And so what you might see more commonly, so I write here CF, that means compare, right? Compare with, so it's an abbreviation for compare with, like IE or whatever. Yeah, so often you'll see stuff more like this with the overline. Yeah, that's more common, but the problem is we've got so many lines knocking around. Yeah, I said this in the tutorial. This should be in the tutorial. If you've got this and you've got the underlines for vectors and matrices and things of fractions, right? There's just too many lines. So this angle bracket notation I just find more helpful when we're writing vectors and matrices by hand, but this overline is more, I would say, is more common as notation. Yeah, so it's just intended, so it's just intended to do the same thing as the overline, right? But it avoids there being too many lines of different kinds knocking around, because we're not using angle brackets for everything else. Yeah, we have round brackets for vectors, square brackets for matrices in general, and these angle brackets can be some properties. Okay. Like I said, I'd like to write this. If any of you kind of tech-savvy youngsters can work out how that screen's supposed to move, that would be great. But the buttons that say screen up and screen down don't seem to move this. Anyway, right. So of those, the important ones are unsurprisingly going to be the mean and variance. Yeah, or the multivariate generalization of variance. So the sample mean is, and so I'm going to tend to write this as n, right? And then the population mean will be, so the sample properties are going to be Latin, yeah, and the Greek, population properties are going to be Greek, not all the time, right? So this is a sample mean n, which is just the average of the x's, so that's 1 over n, sum from I equals 1 to n of xi, right? And we've learned how to sum vectors, divide them by n. And each of these is a random vector, so this is still a random property, right? So n can have an expectation as well, right? That's one of the things we're going to work out. And then the so the sample variance, covariance, and I'm going to use my own little notation with a d here. So this is n over n minus d times the population average of x minus x minus transpose. Okay, so this is really just worth a bit of thought about what it is, right? So we'll see. You can kind of guess, because we did the univariate case in the tutorial, right? That this d is here because this is actually the expectation. This is actually not going to be what we want, right? Unless we fiddle with the d somehow. Okay. So that's there for that reason. But if you look at this, each of these is a random variable, right? So this is an outer product. It's a matrix, like the matrix in the multivariate normal, right? And so we take off the mean, and then we look at an outer product, so product of every vector, every bit of the vector. So just to give a more explicit what we're doing when we do that, it's again, so putting in the G notation of yeah, okay, and so it'll be obvious why, but we're going to say that S naught is the raw sample covariance and S1 is the unbiased. Sample covariance. Okay. So has everyone got down what they want from that? So let me know if you spotted any of the set buttons around the room. Look like they might do anything to the screen. Okay, so you're going to do the main thing we're going to do on Friday is go through why one of those is raw and one of those is unbiased. Right? That's for the tutorial. So the final thing we're going to do under this, because it's a really useful concept, is centering. So you'll see that in that we ended up with quite a lot of removing means. So we can simplify our working a lot, removing either the sums or the angle, both the sums and the angle bracket, by using matrix vector operations. So if we recall what we did in 1.135, yeah, that you can write the sample mean as 1 over n times the data matrix transpose on a vector of all ones, right? So this is quite a useful thing to work with. And the equivalent way of writing things as matrix vector operations for the covariance involves the centering matrix. So that's H, which is the identity matrix minus 1 over n times an outer product of ones. Okay. And then if you write that out, S is the is this matrix product, yeah, the sample. So that's the data matrix, the centering matrix, data matrix transpose, centering matrix, and data matrix, right? And if you want to count what this does is it acts on the data matrix to take off all of the means, yeah? So this gives you a mean, yeah? And it gives you just the original matrix back, but with all of the means subtracted when you follow it through, yeah? And so that does that work of doing the minus n, yeah. So I leave that as a, I don't write it as a formal exercise, right? But I think it's a good idea for you to try writing that out. If you would like, why don't I write it as a? Why don't I while I'm remembering to update the notes, why don't I add show this to the notes? Yeah, I'll add show this to the problems. Yeah, so we can go through showing that in the tutorial as well. Yeah, because I just realised I think I tend to do that instead of the main problems. Okay, but to see why this is useful, yeah. Let's go something that would be an unbelievably fiddly and is going to be very important for using a lot of the kind of linear algebra results when we want to do things like principal components, which is the sample covariance is positive semi-definite if n is bigger than d, yeah. So proof, recall, definition 1125, yeah, which is what is of what being positive semi-definite is, okay, and consider arbitrary vector not equal to 0, yeah. Then x is the x. Okay, so we're going to call this equation 2, 6, 3, and this is 2, 6, 2, yeah. Again, some of the please do look out, because with these notes moving online and offline, right? There's some of these have gone lost. I'm trying to use tech referencing, right? When you put something into slides, it's very hard to keep the referencing, move it off slides. So you so if there's one of these that refers back, I do lots of labeling stuff in the course because there's so many things that you need. You just have to like label them, have to have names, right? But yeah, if you go back and I go, that doesn't point to something that looks sensible, do let me know. And it's probably going to probably moving stuff onto slides and off slides, right, for hybrid teaching. Okay, so let's write out in full. That's from this equation. That's by 2, 6, 3. Yep. So then that's 1 over n minus d t. So it turns out that h squared is equal to h. We're going to show that in the problems. So I'll say that's problem Q3. Yeah, so we're going to show that shows that h squared equals h. Yeah. Okay, and then that's equal to 1 over n minus d x transpose x. Yeah. And that's by problem 2.3 showing that h transpose equals h. Yeah. But if you look at this and call that y, then that's y transpose. So that's equal to 1 over n minus dy transpose y, where y equals hx, big X, little x. And that has to be bigger than or equal to 0, since y is at a squared length. Yeah. Okay, so that was so if you imagine trying to show this with writing out all the sums, right, that's going to be really difficult. But what you can do is you can accumulate the results about the symmetry matrix, and that's quite easy. And that's going to be important because it means that for any sample, the eigenvectors and eigenvalues are going to exist, and they're going to have nice, nice properties, right? And that's also true of the population. The multivariate normal requires that, right? What this is saying is when we have a load of samples from any distribution, and particularly multivariate normal, it's going to have sort of nice properties, right? So, are there any questions